Hello everyone, thank you for joining today's session. In this class, we'll try to understand some basic concepts of circular motion and how the acceleration and velocity parameters govern the overall motion of a body when it's moving in a circular fashion. Okay. When we tried to study Newton's second law, we derived at a very wonderful conclusion that when the velocity of any body is changing, of course it's changing with respect to time, but one thing is sure, if velocity of any body is changing, there is a net non-zero acceleration acting on the body, isn't it? When there is a net non-zero acceleration acting on the body, which means there is a net non-zero force acting on the body. That force may come from different aspects. It depends on field attached to what body, whether it's touching any body or not, that body is rigid or not. Different factors try to govern the different forces, and through different forces, we try to analyze the overall motion of a body. Okay, overall state of motion of a body. Okay, now what exactly happens in circular motion, that we will be studying today. So let's start. Let's say a particle is moving in a circular fashion. Let's say this is a circle. Let's say the particle is going in this sense. At this instant, the velocity vector is here. At this instant, the velocity vector is here. At this instant, the velocity vector is here. And at this instant, the velocity vector is here. One thing is sure, even if magnitude may or may not change, one thing is sure, direction is always changing. Now we define velocity as a vector quantity. When we are defining velocity as a vector quantity, because the direction is changing, we say that v vector is changing. For a particle which is moving in the circle, let's say the circle is having radius r. For a particle which is moving in the circle, velocity vector is changing. When velocity vector is changing, this implies that acceleration vector is non-zero. The velocity vector won't change. We won't have a question of having acceleration vector. But one thing is sure, that because acceleration vector is there and acceleration vector is present because of velocity changing, that means there is a net non-zero force acting on the body which is having circular motion. A net non-zero force acting on a body performing circular motion. Now we studied in motion 1D that let's say a velocity vector is pointing like this, acceleration vector is something like this. This acceleration vector can be resolved into two components. Let's say this angle is theta, one which is a cos theta and one which is a sin theta. We know clearly that is a cos theta will try to change the magnitude of v and a sin theta will try to change the overall direction of v. Okay, so if any particle which is having a motion in this sense, acceleration of that particle is like this. A cos theta will always try to, the acceleration which is along the direction of velocity will always try to change the magnitude of the velocity, and the perpendicular component will always try to change the direction. In this, we know that magnitude may or may not change, but one thing is sure, direction is changing. So in this also, we can resolve the acceleration into two components. One which is exactly perpendicular to the velocity and one which is along the velocity. One which is along the velocity, that is called as AT, that we'll study later. That is called as tangential acceleration. Tangential acceleration. One which is perpendicular to the velocity is called AR, radial acceleration. Particle may or may not have tangential acceleration for a uniform circular motion, but particle will definitely have radial acceleration. Our job is to somehow find the magnitude of radial acceleration. For that, I'll take a special case. Let's take that as a special case, something like this. There is a particle having circular motion. This is our coordinate axis. Let's say this coordinate is, let's say this angle is theta. Particle right now has reached here. It is moving in this sense. Let's say the speed is v and it is angle and it is going tangentially at this point. How do I write the coordinate of this point? Let's say the radius is r. We know the coordinate can be clearly written as r cos theta comma r sin theta. correct? And how do I write a velocity vector? See, velocity vector will have two components, right? This angle is theta, this is also theta. This is theta, 91 is the theta. So V cos theta is here and V sin theta is here. Okay. So how do I write a velocity vector? V cos theta j cap in plus y axis minus V sin theta I cap. This is the velocity vector. Here V is what? Constant. Because I have taken a special case. It is a case of uniform circular motion. Uniform circular. I have to find dv by dt. Why? Because we know that dv by dt will give us acceleration. And because here I have assumed v constant, whatever acceleration that I'll get will be perpendicular. Okay. Clearly you can see the velocity vector will always turn in the direction where the acceleration is perpendicular. So one thing is sure that the acceleration is perpendicular, which is radial acceleration, has to be inward pointing, right? Only then the velocity is turning towards the center. When the velocity vector is here, it is turning towards the center somewhere here. When the velocity vector is here, center is somewhere here. So it is always turning toward the center. That's why the radial acceleration will definitely be inside. How do I find this radial acceleration? Just differentiate this equation. So what do we write? dv vector by dt will be equal to v is constant, so no issues of differentiating v. What differentiation of cos theta is minus sin theta, and we are differentiating with respect to time. So this will become minus v sin theta d theta by dt j cap. Sin theta differentiation is cos theta, and because it's theta, we'll write d theta by dt more. So this will become minus v cos theta d theta by dt I cap. Okay. What is common here? V is common. D theta by dt is common. What we are left with? We are left with minus sin theta j cap minus cos theta I cap. Now you can clearly see, so this is minus cos theta I cap. You can clearly see that this vector, this unit vector is what? R cos theta, not unit vector. The position vector is R cos theta I cap plus R sin theta j cap. So R cap will be equal to how much? Cos theta I cap plus sin theta j cap, just a unit vector. So can I write this as V d theta by dt into minus R cap? Because it's exactly negative, right? Cos theta I cap minus cos theta I cap, sin theta j cap minus sin. Okay. So one thing is sure that the acceleration is always pointing inward, as I told. You can imagine it physically also, and mathematically you can derive the same quantity also. Okay. Which means what? We are sure that there is a non-zero acceleration vector acting perpendicular to the velocity with always pointing itself inwards. Okay. This acceleration vector will be called as radial acceleration. How do I write the magnitude of it? AR magnitude will be how much? What is the magnitude of this vector? V d theta by dt, right? Now when you are studied in motion in 2D, when you study the basic equation of angular displacement and angular velocity, we know that d theta by dt can be written as angular velocity. So there is a radial acceleration of magnitude. Either you can write v into omega, or what you can write? You can write omega equal to v by r. So this will become v into v by r, which is v square by r. Or you can write v equal to omega r. So this will become omega square. All three are the one and the same thing. V into omega is equal to v square by r equal to omega square. So there is a non-zero acceleration which is called as radial acceleration for any particle which is having circular motion. Okay, it's always pointing inward. Now we got AR vector is equal to v d theta by dt minus r cap. If I just multiply both of them with m AR vector should be equal to m v into omega. Forget about minus r cap for some time because it's a vector quantity. I am just comparing the magnitudes. What is m AR vector? Mass into acceleration vector, which is net force, should be equal to mv square by r minus r. So on a particle with respect to origin, if it's having circular motion, there is a net force mv square by r which is always required inside for the particle to have circular. This net force can be provided by all the strings, okay, all the different types of objects. Let's say there is a string, Sometimes the tension will provide net force. Let's say there is a curved surface. Sometimes the normal will provide net force. Let's say there is electrostatic field, or let's say there is magnetic field. Different types of field to provide different types of force. Because this force is radially inwards, this force is called as centripetal force. Got my point? This force will be called as centripetal force. So centripetal force is what, first of all? It's a net force acting towards the center to make the particle go circular. If the particle is going circular, definitely there has to be a centripetal force. Who is providing it? That depends on the situation. Sometimes different types of forces will provide different types. But one thing is sure that should be a net non-zero force acting towards the center for the particle to go circular. Otherwise, the particle will not be able to go circular. Okay, now let's take a very basic example. There is a particle on a table which is trying to go in a circular fashion because of the friction force. So let's say this is a horizontal table. It's a horizontal table. Particle is going with the speed v. Okay, the friction coefficient between the particle and the table is mu. Let's say the friction coefficient is mu. You have to find with what maximum speed that the particle can rotate so that it doesn't slip off. So here, if you draw the free body diagram, and let's say if I look it from here, mg is downwards, definitely. N is upward, definitely. Friction force should act along the direction of plane. It's a planar force, right? Friction is always planar. It's always along the plane of the body in motion. Okay. So when we draw friction force, here the friction force will try to help the particle go in circular fashion. So friction will be pointing actually inside when the particle is going like this. So if I draw the friction value, what will I write? This force, net force, should be equal to mv square by centripetal, m into v square by, let's say the radius is r. Now, this has to be equal to f, right? For the particle to go circular, this f should be the friction that is getting applied on the particle should be less than the maximum value of friction, which means that this friction should be less than what? Mu into n, which is mu into mg. So what will I write here? See, f less than mu mg, and we know whatever is the value of f, that is equal to mv square by, only then the particle is rotating, which means what will I write? Mv square by r should be less than mu mg. M and this m got cancelled. What we are left with? V square less than mu rg, which means what? V less than root of mu. So what is the maximum speed? The maximum speed is root mu rg. So the particle which has to turn, it has to turn with the maximum speed of root mu rg so that it turns perfectly. That's why you might have seen in curved roads they defined speed limit. When the road is horizontal, they'll definitely define a speed limit. One thing is sure, see, this speed limit v is independent of mass, right? So the speed limit v is independent of mass. So when the speed limit is independent of mass, what we can say about it? No matter which vehicle is turning, speed limit won't change. So even if you are turning a bicycle also, or if you are turning a truck also, or a car also, speed limit doesn't change. Okay. One more very good application of circular motion is speed breakers. What exactly happens in speed breaker? Let's say you might have experience of riding two-wheelers, right, or any vehicle for that matter. We know that on a road there are two types of speed breakers. One which is a little bit wide, and one which is narrow, very thin. Now, one which is very much wide, here the radius is big, right? Either you can take this value, whatever you want to get. So let's say the particle or the vehicle has reached here, mg is here, n is upward. What will I write? The particle has to accelerate inside towards the circle, right? So mg minus n should be equal to m v square by r. Okay, and here let's say the radius is small r. Okay, N is up, mg is down. Again the same equation. Mg minus n should be equal to mv square by r. Okay. Now, what will I get from here? N should be equal to m into g minus v square by r. N is equal to m into g minus v square by r. Let's say the contact finishes. The particle loses contact with the ground, because what happens is speed breaker. You know that if you make the vehicle go very fast from the speed breaker, the particle will jump. When the particle is jumping, suddenly what happens? Normal becomes zero. So when normal is becoming zero, here what we'll get the equation? We'll get the equation of v equal to root rg, and here what we'll get? V equal to root of small rg. Which radius is more? This one is more, capital R is more, or small r is more? Clearly from the diagram you can see capital R is more. So when capital R is more, if you have a vehicle at 50-60 km per hour, you can make the speed on an average 30-20, because your speed value for the particle to not jump is little bit more than the speed value of this one, right? Here the radius is more, that's why the speed limit is more. So let's say if you are driving at 50-60, you can lower it to 30-40 also, that is also permissible. But because this is a very small speed breaker, suddenly because of small r value, V has to become very small. If V is not becoming very small, the particle will jump. So that's why, if you observe carefully, the wide speed breakers, there you have to apply less brake as compared to the thin speed breakers. Getting my point? Wherever there are thin speed breakers, there you have to apply more brake. You have to lower the speed more, because this condition has to be fulfilled. Suddenly, if the normal will become zero, the vehicle will jump. We don't want that. Okay, this is a very good example of circular motion. The same concept they use in the construction of bridges also. Okay, either convex or concave. Okay, so yeah, that's it about today's class. Hope you have understood each and every concept. Okay, thank you.